Today we're going to talk about two categories. Two categories are a generalization of categories where we don't just have objects and morphisms, but we also have morphisms between the morphisms. Now the primordial example of a two category is categories, functors, and natural transformations. So just like the primordial version of a category is a set, the sort of prototype version of a two category is a category. Now there's a note here that we're only going to do strict two categories today, which means that things are going to be holding, axioms are going to be holding on the nose rather than up to isomorphism, which is a little bit immoral of us, but actually two categories are very useful, so we're going to be immoral to be useful. Right, so what's two category? Well, first of all, let's remind ourselves what a category is. Now, you might think this is a bit strange, since we all know what a category is, but it can be useful to think about it in a particular way so that the generalization looks particularly natural. So here's the definition of a category. A category, well, I'm going to do small categories because I want to use the word set all over the place. A small category is, small category C, is given by a set of objects, and for all pairs of objects, let's say x and y, a set of morphisms. Now, we also have, of course, identities in composition, so we're equipped with identities, which means that for all x in our object, we have a function from the terminal set to the set of morphisms. Of course, because this is from the one element set to this set, all this does is pick out a morphism from x to x, which is going to be the identity. We also have composition, which says for all x, y, and z in the object of C, a composition function. Now, what does this look like? Well, it takes morphisms from y to z together with morphisms from x to y and sends them to morphisms from x to z. So what that does is that it takes a pair, a composable pair, and sends them to their composite. We have axioms, and those are the unit and associativity laws. So that's the definition of a category that we all know and love. So what are we going to do to make this into a two category? Well, we're going to categorify it, which means that we're going to take this set and turn it into a category. Now, if that turns into a category, then some things are going to turn into functors, because look, if this is a category, then this is a category, which means that this is going to have to be a functor, and this is going to have to be a functor. And then we're going to keep the same axioms. So let's just sort of cheat slightly and modify this board. So what's a two category? A two category, a small two category, we still just have a set of objects. Then instead of this set of morphisms, we have a category of morphisms. Instead of this function picking out an identity, we have a functor, where now this one, which was the terminal set, is now the terminal category, and instead of a function giving us composition, we're going to have a functor giving us composition. So there's the definition of a two category. It's perfectly straightforward, isn't it? Okay, so now I'll unravel it a bit so we can see what it's actually given us to turn these things into categories and functors instead of sets and functions. Incidentally, if you're wondering why I didn't turn that set into a category, well, that's a very profound question. And we'll later see that if we had done that, we'd have got something different. Not bad, but different. Right, so let's unravel a bit. Unravel. First of all, the point is that the morphisms we have a category. Not just a set, but a category. Like that. So what this means is we've got objects which just as before are supposed to be things going from X to Y, but now we've got morphisms in this category as well, which means that given one morphism from X to Y and another one, so these are objects in this category, we can have a morphism in the category, which is what we're going to call a two-cell. So this is where we get a little bit higher dimensional, because we've got this thing that sort of fills in space in between this path and this path. Now, this is a category, so of course it's got composition as well. And what does composition look like? Well, if we got a morphism from F to G, a morphism in the category, this Hom category from F to G, here it is, and another one from G to H, so they're composable, well, we get a composite which goes all the way from F to H. All the way from F to H, and this is called beta composed with alpha. And that's what we're going to call vertical composition, because we're actually going to have a composition in the other direction as well. So this is vertical composition. Now, so much for the underlying data. We've now discovered that we've got 0 cells, which are what we used to call objects X and Y. We've got 1 cells, so those are the X and the Y. We've got 1 cells, which go from X to Y, and we've got 2 cells, which go in between 1 cells. Now we've also got this composition. We've got this composition functor, which is rather interesting. Composition is a functor now. So it goes from, let's write it up again, from there to there. So what does it do on objects? On objects, it takes something from Y to Z and something from X to Y, let's call this one G, and this one F, and it produces for us something from X to Z, which we'll call, of course, GF. No surprises there. Now what does it do? That's what it does on objects. What does it do on morphisms? Okay, these things are categories, so there are morphisms as well. So what this is telling us is if we've got a morphism from G to G primed, which we might call beta, and we have a morphism from F to F primed, which we might call alpha, we have to produce something from, well, what's the source of it going to be? The source is going to be the composite along the top, because that's what functors do. Right? The source of the image of this morphism is the image of the source, and the target of the image is the image of the target. So that says compose G primed with F primed, and we've got to get something going in the middle, which we're going to write as beta star alpha. And this is called horizontal composition, because what we've done is we've taken 2 things that can be pasted this way, and we get something that goes like that. So this is called horizontal composition. Just like horizontal composition of natural transformations. Whereas the other one was where we took 2 things that we could paste together like that and produce something like this. So that was going to be called vertical composition. So what we'll do next time is we'll have a look at how the functoriality of this functor gives us the interchange law. Today we're going to look at the middle 4 interchange law for 2 categories. Now, what we're really going to do is we're going to show how it comes from the functoriality of this composition functor. Remember that these in a 2 category are categories. We've got a category of morphisms from any object to any other object, and composition is then a functor. On objects, it takes a pair of composable 1 cells and sends them to a composite. And on morphisms, the morphisms in the Hom category are the 2 cells in our 2 category. So it's going to take a pair of 2 cells that are horizontally composable and send them to their horizontal composite. Now what we're going to show is we're going to look at what functoriality means here and show that it precisely corresponds to the middle 4 interchange law that we saw before when we were doing natural transformations. The key to seeing how this corresponds to the middle 4 interchange law is to remain calm and possibly give yourself a bit more notation. So let's call this functor phi. And now remember that this is a morphism in this product category, which we could call, it's the pair beta alpha. So this gets sent to, we're going to apply the functor phi, which gives us phi of beta alpha, which in fact is what we were previously writing as beta star alpha. So to see what functoriality is, we have to take a pair of composable morphisms in here. Say, we might have beta primed, alpha primed, which we can compose with beta alpha, and we have to show that phi of the composite equals what we do individually, phi of beta primed, alpha primed, composed with phi of beta alpha. So now let's look at what on earth this beta and alpha and beta prime and alpha prime would be. So let me just leave that up there for a second and take this away. So if these are going to be composable, what that means is that beta is something that goes like this, beta, and beta primed has to be composable with it, beta primed like that. And then this is going to go from, this is the part that goes from y to z. We've also got to have from x to y something that goes from, see, I think I've written this the unhelpful way around. I'm going to write it the helpful way around. We've got three objects, x, y, and z. And we're going to have, first of all, our pair alpha beta here, and then we've got our pair alpha primed and beta primed, okay? And so their composability in the product category means that alpha primed and alpha are composable, and beta primed and beta are composable. Now let's see what this formula says. So on the one hand, we've got to compose in the product category. So how do you compose these two morphisms in the product? Well, you just compose them pointwise. So what this actually is phi of beta primed composed with beta, comma, alpha primed composed with alpha. Okay? And so what is that? Well, on the one hand, we've got beta primed composed with beta, which is this vertical composite. Beta primed composed with beta. And we've got this vertical composite alpha primed composed with alpha. Alpha primed composed with alpha. And now we're going to do phi on them. And what happens when you do phi on them? It says that you take the horizontal composite. So that's what this left-hand side is. Now what about this right-hand side? This right-hand side says do phi on beta primed and alpha primed, which says take the horizontal composite of beta primed and alpha primed. And then it says, on the other hand, you're going to do the horizontal composite of beta and alpha. And then finally, you're going to do this composition here in the HOM category, which means you're going to compose vertically like that. And so what functoriality is saying is that doing vertical composition first and horizontal afterwards is the same as doing horizontal composition first and vertical composition afterwards.